Hello students, in this lecture we are going to study the wave-particle duality. Particularly we are going to see the two experiments, the double slit experiment and the photoelectric effect. So the learning outcomes are, you will be able to explain the concept of wave-particle duality with experiments, and you will be able to apply the de Broglie formula to find out the wavelength of objects. Let us first recap the previous lecture. We have studied the introduction of quantum mechanics by starting with the concept of wave-particle duality. We studied that waves are some periodic variation of a quantity, such as water waves are the periodic variation of the height of water, and light waves are periodic variation of electric field. Light waves have both magnitude and direction. Waves have certain properties such as period, wavelength, and speed. The speed of all electromagnetic radiation is a constant, that is 3 into 10⁸ meter per second. So now let us start with the experiment which is commonly called as a two-slit experiment or the double slit experiment that actually proves that light is behaving as a wave. So in this experimental setup you have a light source which is particularly a monochromatic light source. That is, it has a wavelength that is single wavelength. In this particular case, let's suppose this light is of 633 nanometer. Let's suppose that. Now the second step is that we put a thin film of metal with two holes in front of this light source. So these two holes are called as the slits. These are small slits and they are actually at a very small distance from each other. But just for this figure I have put them at a far distance, but actually in the actual experiment they should be at a very small distance. When the light passes through these two slits, what do you expect? We expect that light will pass through these two slits and through these two holes, and it will form two light spots just in front of these two slits. If the slits are 0.02 inches from each other, then these two spots should be at the same distance, that is 0.02 inches on this screen which is placed just behind this slit. But actually we don't see the two bright spots. We see a series of bright spots with the dark region in between these bright spots. The central spot is the brightest one, and as we move away from from the central region, then the spots they become lighter and there are dark spaces in between these two spots. So what is the phenomena which is happening in between this region, and why we are not seeing only two spots, we are seeing a series of the bright spots on the screen? So this is actually because of the special property or special behavior of the light waves, which property is called as the superposition. So what is superposition? Let's suppose if we have one wave like this red wave, and we take exactly the same wave like this and we put in the same space as the first wave. The two waves are exactly in the same space and they are placed like that. The trough is just exactly over the trough and the crest is exactly over the crest. So if we place them exactly in the same space, what will happen? The waves have this property that these two waves, they will interact with each other and they will superimpose to get a bigger wave. And a bigger wave like this will be obtained by the superimposition of these two waves if they are exactly on the same position. This superposition is now called as the constructive interference because it is positive interference and the wave is getting bigger. It has bigger amplitude on the positive side and the bigger amplitude on the negative side. Now what happens if we have the first wave and we place the other wave in such a way that the crust and the trough overlaps? They are in the same space, but they are placed in such a way that the crust is overlapping with the trough of the first wave. Now in that scenario, these two waves will interact with each other and they will cancel out each other. And as a result of this, cancelling the crust and the trough, we get no wave and a straight line like this is obtained. The intensity of the wave has become zero. This kind of interference or superposition is called as the destructive interference because they are destroying their positive and the negative amplitudes. So now we are going to use the water waves to try to explain it, because we can actually see the water waves and we cannot actually see the light waves. That's why we are going to apply this constructive and destructive interference scenario on the water waves to understand it better. On this side you see there is a single source of water waves in the center and it's producing water waves with the crest and with the trough like this. So it's a water wave source. Water waves are coming from a single source. Now let's suppose if we bring another source of water waves closer to this one, like this figure. Here is the one source of water and there is another source of water waves. Now when the waves are produced, they can interact with the waves of the other source. Again, they are interacting in this region, in the central region. And here we are observing the phenomena of the constructive interference and destructive interference. You see at these points, the depressions, these are all the points of the constructive interference where the trough is meeting with the trough of another wave. So here also you see the trough of the one wave is meeting with the trough of the other wave. The trough of the one wave is meeting with the trough of another wave. Similarly, if you see these bright spots, these are also the points of constructive interference. Why? Because here the crest is coming from the one wave and the crest is coming from the other wave, and they are meeting at this position to form a constructive interference point. Now where is the destructive interference taking place? If you look at certain other points like this one, here you see this is the crest of one wave coming here, and at this point you see the trough of the other wave is coming here. So this point where crest and trough meets, it causes destructive interference. So whenever we have the two waves and the points where the destructive interference takes place, we see the dark spots on the screen, and whenever we have the constructive interference, we see the bright spots on the screen. So this was exactly what was happening in the case of the light source with the two slits. These are the kind of two slits which are emitting the light waves, and the light waves are interacting and producing the bright and the dark spots. So this was showing us that the light is actually behaving as a wave. The interference phenomena was actually to show that light was behaving as a wave. Now let us see another experiment where we can see that light can also act as particle. And this experiment is commonly called as the photoelectric effect. So this photoelectric effect was observed just after the discovery of the electrons. And what is this photoelectric effect? We simply have one metal plate, and if we shine some light on it, shine some light of the specific frequency, that is of the specific energy, then we see that electrons can be emitted from the surface of the matter. The only condition is that this frequency of light must have a certain frequency which is called as a threshold frequency or nu naught. If the light has lower frequency which is lesser than the threshold frequency, then no electrons are emitted. So this EI, the energy of the photon or the frequency of the photon should be greater than or equal to the threshold frequency or phi. So this energy, it actually depends on the metal. Some metals emit electrons with a lower energy of light, and some of the metals, they emit electron with a higher frequency or higher energy light. So for this particular metal, nu naught is the threshold frequency, and below nu naught no electron will be emitted. So this is simply the photoelectric effect. We must have a metal light coming in and the electrons come out. This phenomena, we can also represent it graphically here in this diagram. If we plot the number of electrons on y-axis and the frequency of light which is coming on the x-axis, then we see here at the zero frequency there is no electrons, and as we increase the frequency of the light, at particular frequency of light, we see the electrons are coming out of the metal, and this much number of electrons are coming. Now if you increase the frequency of light, use another light of the higher frequency, then the electrons will come out, but the number of electrons will remain same. So the frequency of light is not going to affect the number of electrons. And we are going to see that this frequency of light, that is increasing the frequency of light, will only affect the energy of electron, not the number of electrons that we will see in the later slides. So also we are going to see now that how this experiment proves that light is acting as a particle. So some of the very surprising observations because of the photoelectric effect. Number one is the energy of the electrons that were coming out was measured, and it was plotted versus the frequency of the light. And it was observed that if we increase the frequency of light, for example, if we are using red light before and then we are using the blue light, and if we are increasing the frequency of light, then the energy of electrons was increasing, and we had a linear relationship like a straight line coming for this graph. So this was the experimental observation in the photoelectric effect. Before this experiment, in the classical physics, we do not have any relationship between the energy of electron and the frequency of light. So this relationship only came in the photoelectric effect. There was no such relation in the classical physics. So this experiment is one of the experiments in the quantum physics. So we can now also plot the kinetic energy of the electrons that are emitted from the metal versus the intensity of light. Intensity means the brightness. For example, we are using the blue light, but at some point we have the dim light, and at some point we have the bright light. So when we have the bright light, it means the intensity of light is higher, but the frequency of the blue light remains the same. So according to this experiment, when they measure the energy of the electrons and intensity of the light was varied, then we do not have any relationship. The energy of the electrons remains same. So it means that changing the intensity of the light source is not going to affect the energy of the electrons. And this one relationship was predicted from the classical physics, although it did not have any experimental evidence, but they thought that the intensity of light increases the kinetic energy of electron, and it has such a relationship like exponential relationship. It was thought, but there was no evidence, and it is actually incorrect because intensity has no relation with the kinetic energy. Only the frequency of light has a relationship with the kinetic energy of electrons. Then we can also draw another graph where the number of electrons are plotted on the y-axis and the intensity of light on the x-axis. So intensity of light does not affect the energy of electrons, but it does affect the number of electrons coming out. So when we have the high intensity of the blue light as compared to the low intensity of the blue light, the number of electrons increases linearly. In the classical physics, there was no such relationship, the number of electrons and the intensity of light. So how it is happening? Basically, the intensity of light is the number of these light photons which are coming. If we have 6 photons of light coming, then we have 6 number of electrons emitted. It means this is the intensity of light and it is directly proportional to the intensity of the electron. However, the energy of this individual electron is only dependent on the frequency of light, not the intensity. If we have 10 photons, 10 electrons will be emitted, but they have this energy which is equal to frequency of light. So intensity is related to the number of electrons and this energy of the single electron is related to the frequency of light, not the intensity of light. So this was actually the photoelectric effect which provided the basis that the light might be behaving as particles, and these particles were named as the photons or quantum. These relationships that we have studied, that is the intensity of electron, number of electrons, the energy of electron and the frequency, etc. They can only be explained by assuming that the light is acting as photon and it is the packet of energy, and the frequency of light determines that what is the energy of each packet. It's not acting as a wave here, it is acting as a particle, and these particles are called as photons or quantum. So this experiment basically proved the photon nature or the particle nature of the light waves. Now Einstein did some further experimentation. What he did, he took several metals like rubidium, potassium and sodium, and he performed the photoelectric effect on different metals. And definitely rubidium has a different threshold frequency, potassium has a different threshold frequency, and sodium has a different threshold frequency. The energy of the electrons emitted was plotted versus the frequency of light. So a linear line was obtained because the energy of electron is directly proportional to the frequency of light. Since this is the straight line equation, we can find out the slope of this equation. According to the straight line equation, y is equal to mx plus b. Then if you find out the value of x, the slope for all three lines was equal to the value of 6.626 into 10 raised to the power minus 34 joule second. So this slope was same for all the metals, and he called this number as a constant, which is called as a Planck's constant. The intercept can be obtained if you extrapolate this line to the y-axis, and this intercept is equal to the minus h nu naught. Minus because it is going into the negative section. So we can write down the straight line equation here. Y is equal to mx plus c. We are plotting on the y-axis the kinetic energy, so we can write it down kinetic energy. X is actually the nu. M is called as a Planck's constant h, so we have written as h nu. Mx is equal to h nu. And the intercept is negative, so we have written the negative sign, which is equal to h nu naught. He observed that for all the metals, the intercept was coming out to be h nu naught. So this was the equation that was derived from the photoelectric effect. Kinetic energy is equal to h nu minus h nu naught. So this kinetic energy can also be written as the energy of the incident photon, Ei, and h is the Planck's constant. Then from the experiment, the Einstein postulated some of the points. He said that the energy of photon is proportional to its frequency. Here, from this equation, he said that this is the energy of the incident photon and it's equal to Ei, can be represented by Ei. So this was one of his observations. In the classical physics, there was no relationship between the energy and the frequency of light. There was no relationship like that. So this was the first time that a relationship was given between energy and the frequency of the photon, like this, E is equal to h nu. Then he further stated that light is made up of energy packets called photons. And this provided a new model for the photoelectric effect, where the incident light frequency h nu is equal to energy of the incident photon. H nu naught is the threshold frequency, that is minimum energy required to eject an electron from the surface of matter. Let's suppose in this diagram this is the metal surface and you require a minimum energy to eject the electron from the surface, where here at this point the electron is free from the metal. And this energy is called as a threshold energy, or phi. It is also called as a work function in some books. Now if the coming photon has a higher energy, then what happens? That the electron is emitted and the extra energy above the threshold energy is converted into the kinetic energy of electron. So this extra energy of the photon is going to the kinetic energy of electron. So in the next lecture we are going to see that how matter can behave as a wave, and we will see the